Sure.
Yeah. Okay. Welcome, Gary, to this special DMN meeting in the summer period to explain your recent work on the emergence of nonlinear friction from quantum fluctuations. Please be our guest. The screen is yours.
Okay, great. Thanks, Peter. So this is, let's see, you guys can hear me, right?
Yeah, I see your mouse.
Okay, yeah, and Keynote doesn't have one of these laser pointer things, so you guys will have to keep your eyes sharp for a little mouse. I've Googled this, there's really no solution, but maybe someday. In any case, so so I was just having a Zoom coffee with Peter in June, and then we came up. We were discussing a bit about physics as well, and we started talking, and I was mentioning this funny work that we've done recently, looking at superconducting circuits, so maybe a bit of background on myself. I actually started my research group in Delft on nanomechanics, and then recently and has shifted a bit to superconducting circuits and nanomechanics, which is still a main focus. But we also my group, but we also do a lot of work now on superconducting circuits themselves. And so I'm going to show some work today that basically came up as a funny observation when we were studying this device here. So this device you see in the background is actually a superconducting microwave resonator. And if you look carefully, there's a little thing over here. It's actually a superconducting microwave resonator that contains a squid. And it turns out that we did what we usually do. We look at the response of this guy and turn up the power. And then we saw a funny thing, which was sort of nonlinear damping. And then for 5 years, we sat around thinking about, oh, that's funny. I wonder where that came from. And then in the end, it turns out that my PhD student, Mario, was working on quantum simulations. And it turns out that we could explain all this funny nonlinear friction, nonlinear damping we saw by purely quantum fluctuations. And that's what I'll try to tell you about today. So let's say this is the outline of my talk. I want to start with a bit of a background introduction, for many of you perhaps very familiar, about nonlinearity in nanoelectromechanical systems, nanomechanical systems, and quantum circuits. It turns out they're pretty much identical, just have different origins and work in different regimes. I'll give a bit of an overview of my understanding, actually, at least of nonlinear damping that we've actually encountered in the past, both in my work in carbon nanotubes many years ago, and now more recently in superconducting circuits. It's actually well known in superconducting circuits that there are nonlinear damping effects, but they're of a different type. And I'll tell you today about a very strange type of nonlinear damping that we observed in these circuits. And then finally, I'll continue to the main result, which is the observation of this nonlinear damping, and then the things that we did to show that this actually is a purely quantum effect. And please, if there's nothing, my aim is to make this as clear as possible for everybody. So if there's something that's not clear, feel free to stop me and ask a question. That's my aim, is for you guys to get the most out of this talk, let's say. So I'll start with a little bit overview of my understanding of what I'll call conservative nonlinearity. So my first encounter with conservative nonlinearity was in nanomechanics when we were working on carbon nanotube resonators. And I usually think of these, most of these things are harmonic oscillators, which means we have some sort of force acting on a mass that's bringing it back to an equilibrium position, and that force is proportional to the displacement from equilibrium, and that gives you this force is equal to minus kx. Of course, that's some sort of approximation, and in real life there are higher order terms. It turns out that the next important, and if you want to get technical, dynamically important term is this term x to the cubed. And so the first important correction to the dynamics of a linear harmonic oscillator is when you add a restoring force term that goes like the third order of the power. If you do this, you get something called which I at least call, and many people call, the Duffing oscillator. This is named after George Duffing, who was actually a German audio engineer. And what it means is that the force, a linear restoring force, would be this force equals kx. And if you add this cubic term, then what happens is either as you extend the springs further, it starts to get softer. That's when alpha is less than 0. And that means that it doesn't apply as much force as you think it would. The other type of correction to the linear response is when alpha is greater than 0, that gives you this hardening term where the spring gets harder or stiffer. Okay, so what are the consequences of that? The consequences of that, which you may have seen in your own measurements if you work in nanomechanics, is that when you start to drive the system harder, if you apply a larger oscillating force to your mechanical resonator, then what you will see is that the line shape of your resonance is no longer an iso-Lorentzian peak, but starts to tilt over. This is what we sometimes colloquially call the shark fin. And if you drive this Duffing oscillator hard enough, what happens is that this folds over on itself, and you get a region of metastable states here. Actually, you get 2 stable states for a given driving frequency and driving force. And which one you end up with depends on the way you approach this point. If you, for example, if you're sweeping the frequency from below to up, you typically, in this case, would follow the high branch. If you're sweeping it from up downward, high frequency to low frequency, a constant force, you would follow this low branch. And when this in this region, actually, if you did a forward and reverse sweep, you would see hysteresis. You would follow this up, and you jump down, and you go up further, and you jump back and jump up and down. And on this point at which these 2 stable solutions appears what people call often the bifurcation point. Okay, so I have no idea if you guys are following me or not, because but that's a funny thing about giving video talks. So I'll just continue on.
This is quite clear, I think, Gary.
Good, great. I'll just keep going. If I start to lose you, please let me know. I'm working a bit blind. So, okay, so this may be very familiar. What is maybe, so, I mean, lots of people see these types of things in your measurements, and we saw them a lot. And what was maybe not familiar to everyone, or at least it wasn't familiar to me until we started looking at it when we wrote a paper, is that there's, if you look at, well, what Mohanty called normalized amplitude, which is actually something which is called the mechanical susceptibility. That's the amplitude of the oscillator divided by the force that you're applying. Then in the high Q limit, when you're talking about very small deviations from the resonance frequency, then what happens is that what's very interesting is that the peak mechanical amplitude is actually, the peak mechanical susceptibility is not modified by the nonlinearity. In fact, actually, if you divide out the amplitude you get by the force you're applying, then for high Q, then actually this peak just moves horizontally. It's actually a constant amplitude, and that's a useful observation that we learned when we were writing an earlier paper about molybdenum rhenium drums, which we'll come back to in a bit. So this is, okay, so now, so far, this Duffing force is this correction to the linear restoring force. I call this conservative nonlinearity because it is purely proportional displacement and not velocity, and therefore it doesn't cause, for example, extra dissipation of energy. It is actually just sort of a shift of the spring constant. And it's been observed, quite often in nanomechanics. These are not even nearly the earliest observations of these. These were just a couple of nice examples that I found that had nice plots. So this is again from this paper by Mohanty, 2013, where they looked at this nonlinear response of a diamond resonator. And here you see this typical alpha greater than 0 mechanical stiffening. So this has, in NEMS, people can usually get a good handle on the origin of this nonlinearity. One is something called geometric nonlinearity. That's due to the fact that the displacements are not in the direction of the springs. It's a very fun one that I've also learned some interesting things together with Peter recently. But I'll leave that for now. Another common one that you see in electrically actuated nanomechanical systems is electrostatic forces, which are actually an anti-restoring force. And that causes the resonance frequency to bend downwards as you increase the drive power. And this is my first encounter with Duffing oscillators, which is in this work with our nanotube single electron tunneling devices, where they were just super nonlinear. We had to work very hard to stay anywhere near the linear regime. And interestingly, in these devices, we could actually tune the sign of the nonlinearity by changing the gate voltage by a little tiny bit. And this is because we were looking at the interplay of geometric nonlinearity, tension-driven nonlinearity, and electrostatic nonlinearity from single electron tunneling. Okay, good. So that's nonlinearity in NEMS. I want to give maybe an introduction to superconducting resonators, because that's what I'm going to talk about today. So superconducting resonators look a little bit different than nanomechanical systems. This is a typical example of what a superconducting resonator will look like. It's a transmission line that we patterned. This is a device from our group, and this is a transmission line that we patterned in a superconductor on a chip. And we've engineered the length of this to be actually λ/4 at around 5 gigahertz. And so so this, if I look at waves propagating in this waveguide, then they will bounce off each end and form a standing wave, and that standing wave will give us a resonance around 5 gigahertz. We couple these to an external transmission line here, actually in this case capacitively, by having a transmission line on our chip. We send microwaves in over here, and we can, for example, measure the microwaves that are transmitted over there. Turns out if you take all this complicated transmission line stuff, you can map this always near resonance to an LC resonator. So this is actually a inductor capacitor resonator, and this follows exactly the same equations of motions from the nanomechanical resonator, except now for the equations describing the current and the charges on the capacitor. Good. So upshot is that this is a superconducting resonator, and it also behaves just like an LC's mass on a spring. Now, one of the most interesting sources of nonlinearity that we can engineer in superconducting resonators is something called a Josephson junction. To make a Josephson junction, what we do is we interrupt a bit of our superconductor by a very, very thin insulating tunnel barrier. And what happens is that the electrons in the superconductor actually are all occupying a macroscopic wave function, which we can describe with an amplitude and a phase. And there's also an amplitude and phase of the wave function on the other side of the barrier. And what happens is that in this insulating region, there's a decay of the superconducting wave function, and there's some overlap. And if you're a PhD student in 1962, you can describe this in basically what Feynman now write down in about 3 lines of equations. And you can derive something called the Josephson relations, and thereby win the Nobel Prize. What the Josephson relations tell you is they tell you the current voltage characteristics of such a junction. They're actually not explicit. You cannot write the current as a function of voltage. What you typically do is write an implicit equation that describes them both in terms of the superconducting phase difference across this junction. So yeah, and these we can make in the lab. This is what it looks like. So this is, we use a trick called the Dolan bridge, where we make a free hanging bridge of photoresist that is undercut, and we evaporate from one side, and then we have a tilt stage in our evaporator. We evaporate aluminum from one side, and then inside of the chamber without venting, we put a tiny bit of oxygen for about 5 minutes, and then that causes a somewhat controlled oxide to grow on the surface of the first aluminum. And then what we do is we tilt the stage so that we then evaporate from the other angle, and actually underneath the bridge, which would have been hanging in space about here, we get this shadow overlap between the two regions of superconductor that are isolated from each other by this very, very thin tunnel barrier. So what is interesting, I'll slow down a bit, give people time to catch up. And if I hear nothing, I will just continue. Good. I will continue. So what is interesting about this, you can derive this yourself for homework if you want, is that if you take these two equations, you'll find out that the Josephson junction in a circuit, he looks like a nonlinear inductor. In fact, actually, it turns out that the LC circuit you can visualize in terms of a harmonic oscillator. If you plot this as a function of the current or charge on the capacitor, this circuit will have this harmonic oscillator behavior. It turns out that this circuit over here follows a cosine potential. And if you're sitting at the bottom of this well, the first order correction of the cosine potential is exactly a cubic term. And that, quadratic term in the energy, which is a cubic term, say, in the restoring force pushing the particle back to the bottom of the well. And so actually putting a Josephson junction with a capacitor, replacing the inductor with a Josephson junction gives you a source of Duffing nonlinearity. This is actually what people do when they make a superconducting qubit these days. So all of the quantum computers of Rigetti, of IBM, of Google, you can go and buy one from IBM. Apparently now they're starting to sell them if you have lots of money, like Germany or Japan. And if you do that, you will get basically a whole box full of these little Josephson junctions in parallel with a capacitor. That's because the nonlinearity is strong enough that the spectrum of this thing is no longer a harmonic oscillator ladder, but has distinct transitions between 0, 1, and 1, 2. And that is what makes a qubit. This is how you make a qubit, how Google and IBM make qubits, at least. And in the context of Duffing oscillator, the qubit, a funny thing, a qubit actually, turns out if you analyze it, obeys the condition that it is a Duffing oscillator, which is already bifurcated by currents that are equal to the 0-point fluctuations currents in the circuit. So basically, the idea is that a funny observation, just mathematically, is that the quantum fluctuations of the current through this inductor are actually large enough to cause a bifurcation of the classical Duffing oscillator. I don't know what that means, but I think it's pretty cool.
Gary, the advantage for qubits is that you do not accidentally excite it to state 2, right?
Well, that's what you need. So to make a qubit, you need to need to be able to control the state of the system deterministically in the 0-1 manifold, so between the 0 and 1 states. And the way you do that is just by shaking it. You just apply an oscillating force, and actually the harmonic oscillator, the problem with the oscillating force is that, say, by the time you've got 50% of the quantum state up to 1, then some of it already starts to leak to 2. And what's very strange, actually, it's a very interesting one, is that if I take this qubit, which is just a Duffing oscillator, and I start to shake it at its resonance frequency, then what happens is it starts just like the harmonic oscillator starts to get transitioned up to 1, which means it starts to ring up. But then as I keep shaking, it rings itself back down again.
It's like a stimulated emission in a laser, right?
Yeah, it's a bit like that, indeed. It's a Rabi oscillation, right?
Yeah.
It undergoes, so actually even the harmonic oscillator, as part of it is leaking up to 2, some of it is being transitioned back down to 1, from 1 to 0. But the net balance is that you get pushed up and up the ladder as you shake for longer.
Yeah. Yeah, it's very hard to know whether such a resonator is in state 1, 2, or 3. So it's much easier to use it in a quantum computer when it only is in 0 and 1.
Well, I mean, even stronger, you need to be able to program 0, 1, or 0 plus 1, or 0 plus 0.51, or whatever you want. You need universal gates on the block sphere, and that's actually just not possible with a harmonic oscillator, because if I apply a linear, if I just push my harmonic oscillator, the only thing it ends up in is a coherent state.
So you say it's not only, but if you would be able to control it to state 0, 1, 2, or and 3 and read it out,
sure.
Then you could make a multi-state qubit, right?
Oh yeah, sure, yeah, absolutely. But the problem is that, let's say it this way, using let's say the big advantage of a qubit is that you can use a classical thing, which is an oscillating field from your laser or microwave generator, to generate quantum states. Yeah. Whereas I can generate I can generate any arbitrary quantum state using my classical microwave generator, just a classical oscillating field. Whereas with a harmonic oscillator, because if I have a linear coupling to an oscillating field, then all I can generate is the same state I put in, which is a coherent state. Mm-hmm. You can never generate, say, something with a negative Wigner density, if you want to get sort of technical about it. Yeah. And actually, that sort of negative Wigner density is what you need to do quantum computation.
Did you ever calculate how nonlinear mechanical resonator would need to have sufficient nonlinearity to reach this qubit?
Yeah, sure. This very. It's actually a super easy calculation, because what you need to know is that if you know basically you just do first order perturbation theory. That's actually what a transmon qubit comes from. You look at the quantum fluctuations. It'll be super clear at the end of my talk, actually. But you look at the quantum fluctuations of the thing, and you look at how much they change 2 with respect to 1. And if that is larger than the quality factor, if that's larger than the line width, then you can make a qubit. Of course, if I have no damping, any infinitesimally small nonlinearity makes a qubit, right? Yeah. Because the criterion is about the ratio of the anharmonicity, the difference between 0, 1, and 1, 2, compared to the line width of the states.
But wait, you're talking about no damping, but okay, the Q only determines the thermomechanical damping, right? The thermomechanical fluctuations, and not the quantum fluctuations, right?
Well, I mean, whatever the line width is, you have to have the difference larger than that line width.
Yeah, okay, but the line width can be determined both by quantum fluctuations and by thermomechanical fluctuations, right?
Oh yeah, I mean, typically with quantum circuits, you're at high enough temperature, the thermal fluctuations are relevant. But of course, you couple this to a transmission line that goes to your amplifier that you read it out with, and that will always cause some loss. But also, there's more boring sources of loss, like this capacitor has lossy dielectric, and then that dielectric absorbs energy, and then you lose your quantum state.
Yeah. Okay, thanks.
Good. No problem. So let's see, where were we? So then now that's sort of my overview of conservative nonlinearity. And since this talk is about nonlinear damping, I wanted to give a little bit overview of nonlinear damping in nanomechanical systems and quantum circuits. So phenomenologically, I can also add corrections to the friction that my oscillator experiences. And a common correction is something like this: eta x squared x dot. So the normal friction term would just be some coefficient times the velocity, but then this one here also includes this sort of increases the friction or decreases it if eta is negative, increases the friction, changes the friction as my amplitude of my oscillator gets larger. And actually there's a very nice signature of this, which is pretty easy to see. Of course, if I have no conservative nonlinearity and I'm looking at a harmonic oscillator that has purely linear conservative restoring force, but has only this nonlinear damping, then of course it's easy, the thing gets fatter as I drive harder. But life gets sort of more complicated if the conservative nonlinearity is not negligible. The Duffing term is not negligible because you're looking at some sort of weird, actually the width of the Duffing response is just related to how far you're driving it, above the bifurcation, and depends on which direction you're sweeping, up or down. But it turns out that what I mentioned earlier, if you look at the normalized amplitude, aka the susceptibility, then actually you can already directly identify with no fits any kind of nonlinear damping, because the normalized amplitude actually drops down. This is a numerical simulation by the Mohanty group in this paper where they included the nonlinear damping in the dynamics. There's also a very nice paper by Lifshitz and Cross, but their plots are not as nice. So what happens is that actually the amplitude of if you have some sort of damping like this, and as you increase your driving force, then the normalized amplitude, the susceptibility, actually goes down. And you can kind of see this even from the context of a linear oscillator, a linear harmonic oscillator. If you look at a linear harmonic oscillator, you know that the resonant amplitude is not just the force divided by k, which would be the static displacement of a mass on the spring, but is force divided by the spring constant times the quality factor. You have this quality factor enhancement. So it's kind of intuitive that if I divide amplitude divided by force, and well, it's kind of intuitive that the amplitude divided by the force will go down if the damping goes up. And actually, so that's sort of the intuitive picture on why this amplitude drops. And you can actually get a pretty, if you don't have a strong Kerr nonlinearity, you can get a pretty good, actually even with a Kerr nonlinearity, you get a pretty good approximation of the dynamics by just saying that the Q is dependent on the force that you apply, which is not really correct, but gets you a good approximation. This is actually what people call power dependent damping. It's also seen in NEMS, actually. It was actually seen in this paper here, where they observed that this normalized amplitude went down. It was also observed by, in earlier work by, for example, this is the first work at least I became familiar with nonlinear damping from Adrian Bachwell's group, where they showed that, they showed that the width of the peaks goes up as you drive harder in nanotubes and graphene. And these are both cases of what I'll call positive nonlinear damping, which means that as I drive harder, the damping goes up and I get more dissipation. So actually, this is sort of where we got, this is just to highlight a bit of our own earlier work on this. We also ran into this when we were looking at we had this earlier work, we looked at mechanical drums. This is a aluminum drum read out with a superconducting resonator. And we did the same thing, but curiously enough, in this device, we saw something that went the other way. Actually, the responsivity, which is basically the normalized amplitude or susceptibility, if you want to call it that, actually went initially up as we increase the force. And actually, in all of these papers, both ours and the earlier work, people are not really able to draw any conclusive, statements on where this nonlinear damping is coming from. In contrast to say the conservative nonlinearity, which usually can be very well modeled by either the electrostatic forces or tension-induced changes of the stiffness, there's actually no particularly good microscopic model for these. maybe I want to say as well, nonlinear damping is also very commonly observed in superconducting resonators. The people in the superconducting resonator community usually call this a power-dependent Q. And actually, in superconducting resonators, things almost always go the opposite way. So as you drive the resonator harder and harder, then you typically get actually a much lower loss and a much higher Q. Actually, people who work on qubits and superconducting resonators are obsessed with the single photon Q because that's what's relevant for qubits. And unfortunately, the single photon Qs are usually much worse than the high driving limits. They have an interpretation for this. This is actually interpreted in the context of saturation of two-level system losses. So the hypothesis is that there are two-level fluctuators in the dielectric, and as you saturate all of these with high enough power, then they can no longer absorb energy. And so that's my overview of nonlinear damping in superconducting circuits and NEMS. Questions? How are you guys doing?
Ata, maybe you can mention a little bit about your source of nonlinear damping. I'm not sure if Gary saw it, but
indeed. So Gary, there are recent papers also from our group that try to pinpoint the origin of this nonlinear damping scene. Well, first of these kinds is to use some kind of viscoelastic model. And the second is that to show another source, this energy to lead. In our case, it was another mode. So we had a mode that twice the frequency, and this internal resonance caused the nonlinear damping. It was very obvious to show. I think these are two very clearly, both mathematically and physically, clear sources of nonlinear damping.
Yeah, cool.
So I think the viscoelastic term eta, basically the origin of that, there can be multiple origins, microscopic origins that cause it.
I see.
So it can be viscoelasticity of the material, but it could also be coupling to a higher mode, higher frequency.
I see. Yeah. So there's also I don't know if you remember, Peter, we looked at this geometric nonlinearity to understand dissipation dilution. It turns out if you follow that, well, as you remember probably, we're working on writing that up, by the way. We should coordinate and get some feedback from you on it as we prepare a manuscript for like American Journal of Physics or something. But there, you can actually see that the geometric nonlinearity also transforms the linear damping of the restoring springs into a purely nonlinear damping. That's a very interesting one. That's another clear physical origin, let's say, in highly tensioned systems.
Yeah, there's a recent paper that shows that in a silicon nitride membrane resonator.
Yeah, is that from Albert Schleicher's group? Or?
I know the PhD student, it's Letizia Catalini, but I don't know. I don't remember the group.
Okay. Yeah, I know he was mentioning it a few years ago at a conference.
Can you forward it to us, Ata?
Yeah, sure. Yeah.
So, okay. Let me go further though, and introduce you to the stuff that how am I doing for time? Oh, I'm all right for time, I think. Maybe it was a bit slow, but it's okay. So I want to introduce you to a particularly funny case of nonlinear damping that we just coincidentally observed in a device a long time ago, and that we were puzzled about for many years. But then turns out that we had a student who showed that actually this can come from a purely quantum origin, and this is very interesting. So it's a very funny result. It's also funny because unfortunately I lost the reference, but we're making sort of funny devices which are not qubits but very weakly nonlinear. It's a type of corner of superconducting circuits that are not super often studied, and it turns out that we ran into a paper many years ago by a Paris group who also observed it was not a paper, it was a thesis, a PhD thesis where they were like, yeah, we observe this damping, we don't know where it's from, and yeah, maybe it's extra heating, or maybe it's and we were like, oh wow, that's weird, we see the same thing. Okay, but let's go to it. So what is our device? So our device is very similar to the superconducting resonator I showed you before. It's actually got a very large, it's got a very significant geometric inductor with a capacitor. It turns out that this geometric inductor reduces the anharmonicity of the circuit from the junction. We also use a very large critical current Josephson junction, much larger than they do with qubits, and that also decreases the nonlinearity that we add to the circuit. So it's kind of a funny capacitor inductor junction, and we do a very simple measurement. We have a transmission line that it's coupled to, and we measure. We couple it on the side to a transmission line. We measure the transmission that's from one side to the other. So we call this actually a Kerr oscillator. And that's just a bit different terminology people use in quantum optics. It's actually identical to a Duffing oscillator. And in this case, it's a Duffing oscillator that we apply the rotating wave approximation to technically, and that makes it a Kerr Hamiltonian. It turns out that's exactly identical to the slowly varying envelope approximation, which is almost always used for solving the dynamics of Duffing oscillator. For example, this work by Holmes and Rand that I always like to cite from 1975 also does the rotating wave approximation. They just don't call it that. So they're also studying a Kerr oscillator. So this is what it looks like. We have a capacitor over here, and then we have this inductor for various reasons. I won't get into the reason why we put an inductor there, but it's there. And then over here, we have a junction. It's actually not only a single Josephson junction, it's a squid. So it has two junctions in parallel, but we operate this at the point where at the top of the squid arc, so that we can effectively consider only a single junction. This is the same picture I showed you before. This is the device. We have aluminum here. It's made on silicon substrate. These are the Josephson junctions. And actually, as you can see here, the most of the chip is actually a different color. That's because it's made from a superconductor called molybdenum rhenium. The reason for that is that it turns out if you make your whole cavity out of aluminum, it turns out you have very bad, at least we had very bad dielectric losses, which is, of course, not related to the aluminum itself, which is a superconductor, but more the contamination layers underneath it, most likely. But in any case, you can see here that actually most of the chip is molybdenum rhenium, and we have this little contact between the molybdenum rhenium and the aluminum that connects this Josephson junction to the rest of the circuit. So one super important thing that we did in this experiment, which actually maybe didn't come across super clearly in our first version of the manuscript, is that we actually performed an absolute calibration of the nonlinearity of the circuit. And the way we did that is that we did a full simulation of the circuit response and the circuit resonance frequency. Well, let me first say, why is this needed? In principle, it looks like I could just plug this into a circuit simulator, a software simulator, and it'll just give me the resonance frequency, right? In principle, this would be true, except for the fact that superconductors have very large corrections from something called kinetic inductance, and actually the total inductance of the circuit is not only that determined by the geometric shape of the electrodes, but also by the kinetic energy of the electrons flowing in the wires. And that's actually a very non-trivial correction, it turns out, in superconducting resonators, sometimes up to 30 or 40%, sometimes up to 100% even, or near 100%. And so it's actually not so easy to know, in principle, if there's no kinetic inductance, all we would do is simulate this in our software, and then we would measure the real resonance frequency, and then we know our inductance of our squid, and we know all of our nonlinearity. Josephson, once we have the Josephson inductance, the nonlinearity terms are also just directly related to that Josephson inductance. But the problem is that we don't know that so well, because we don't know the kinetic inductance of the film on that run. And so what we did is that on the exact same chip, we patterned devices that don't have Josephson inductions. And using that measurement, we could actually calibrate out the effect of the geometric inductance of the kinetic inductance of the superconductor. In fact, we could calibrate everything out. And then what we did is we did a simulation of the resonant frequency of the circuit by replacing our superconducting junction with a lumped element inductor. And if we do that, we can calculate what the frequency of the circuit should be, and combining that with observation of what the frequency of the circuit was in the device with the Josephson junction, we were actually able to directly extrapolate that to find the exact Josephson inductance that we had in the real experiment. And that will become crucial because that will give us a way to independently, completely constrain our models such that we can actually conclude that all of the things we're observing come from quantum fluctuations.
Gary, why is this only important superconducting circuits? Or is it also, is it because it's the kinetic energy of the electrons is higher?
Well, so very good question. Basically, the reason is that superconducting thin film resonators have very low electron density.
Okay.
And so that's basically why you need to include the kinetic inductance as a large correction.
Okay, so at the same current, the velocity is much higher of the electrons, and therefore mv squared is much higher.
Exactly. Now, of course, I could also actually, this superconducting resonator above its critical temperature would also have just as large a correction to the kinetic inductance. Maybe a factor of 2 different because of Cooper pairs. I'm not 100% sure on that bit. But there's sort of a simple pragmatic observation that when it goes above the superconducting temperature, the resistance gets so high that the quality factor becomes basically 0, less than 1.
Mm-hmm.
And because of that, the kinetic inductance is not relevant because you can't even measure a resonance. Actually, more recently, there's been some work by people trying to look for very highly conducting low density systems to try and observe kinetic inductance in non-superconducting systems. And one of the obvious choices is graphene. And so there's actually been some work, people trying to use graphene microwave measurements to observe the kinetic inductance. And I think they did.
Interesting.
Gary, so quick question with this kinetic inductance, is this something that changes drastically from device to device or deposition to deposition, or can I make 2 different chips and you can kind of use them to calibrate one another?
Naively you would say that it's just going to be related to the electron density, so the thickness should be the only important thing. It turns out it's not so simple because the superfluid fraction is also, well, okay, I don't even know the full details on this one. I'm going to make some stuff up, but it's basically related to the resistivity. So if you have the same R per square, then I believe that it should be pretty comparable. That's my understanding.
So if you just measured this RRR value for both of them, then you know that, and they're the same, then you can say the kinetic inductance is maybe pretty similar. Or is that?
I think probably even the R per square is more important.
Okay.
Than the triple R.
Okay, and so with this one, is this really the calibration without the squid is on the same chip with the squid?
This because we're paranoid, we did this on the same chip even.
Oh, then I think that's as good as you're gonna get, basically. Then, yeah.
I mean, we also looked at different chips, and there's not really. I mean, there may be a few percent maybe 10% variation chip to chip. Related to the process, the different films might have slightly different R per square for the same thickness, so the thickness might be different, or the surface prep might have influenced the first like few nanometers, and the R per square changed a bit. Or
does the variation get worse if you go thinner? More surface
Yeah, probably.
stuff?
I think
Yeah.
so.
Yeah.
My guess is yes. It's one of the big problems that is that when you have if you're doing a big wafer, it varies a lot across the wafer, right? Because the sputtering, that's why people like SRAN are obsessed with having like 8-inch tools, not because they necessarily want to work on 8-inch wafers, but they want to have very high uniformity over a 6-inch wafer or something. Let's see. So now I'm going to then show you some data. So I've already shown you some data, actually. In case you've never done measurements like this in microwave reflectivity, I want to get you familiar with this. So this is actually our resonance. In contrast to what I've shown in the nanomechanical measurements earlier, this is not a peak, but a dip. So I want to get you guys all used to looking at dips. This dip comes about because what you're seeing is actually an interference of the signals that go into your resonator and come out, with those that are directly transmitted from the input port to the output port. So you need to flip your head around, and the height of the peak now becomes the depth of the dip. That's sort of the important thing. And there's actually not a completely one-to-one relation between the two, but that's we can work it out. It's not so hard. So let's take a look at the data then. So this is the data. Basically, the experiment is pretty simple. We just measure the reflectivity of the device, or the S21 of the device, the transmission along this feed line. At the resonance frequency, we see this dip at 5.1 gigahertz. And then the observation is that as we turn up the power, as you see here, we see that of course, it's a Josephson circuit, so it has nonlinearity. It starts to get this slightly shark fin-like shape. But what we can already see is that the depth of this dip is changing. So the dip is not as deep. And that is exactly the same effect as how the work in the NEMS I showed earlier. As you turn up the power, the normalized amplitude goes down, because this is of course normalized. S21 is a normalized measurement. It's the power in divided by the power out, and so this is a little bit like normalized amplitude. And so as you turn up the power, this dip actually, if there was no nonlinear damping and we had only conservative nonlinearity, what would happen is that it would just shift horizontally following this dashed line. But it doesn't, and what happens is it actually starts to become less deep. We can model this, and what we can see is that as we turn up the power, the line width is initially 190 kilohertz, but as we turn up the power higher and higher, then the line width goes up. The damping rate goes up to 295 kilohertz. And this is at very low drive power. So let's say there's two observations. First of all, this is super low drive powers. If you go back to the plots I showed you earlier on superconducting resonators, and the saturation of the two-level systems, the most common source of nonlinear damping in these things. First of all, that's at like 10 to the 6 photons typically, and here we're talking about 3 photons. And second of all, it goes the wrong way. If we were really talking about nonlinear damping from two-level systems, then the minimum, the damping rate would go down, which would mean that in this case, the minimum would actually go down and not up. So it's not two-level systems. Of course, if I drive my superconducting circuit hard enough, maybe I'm exceeding the critical current and starting to generate quasi-particles. But again, at 3 photons, we are absolutely nowhere near that limit. So now, what we did is we said, okay, it looks like nonlinear damping. Let's see if we can fit it with nonlinear damping. That's actually what we did for about 3 years.
Gary, just one question, because are you not talking about the normalized amplitudes here? I guess yes, because it's S21, but the fits, are they from a Duffing model?
those are from, the fits are from a Duffing model that includes nonlinear damping.
Okay.
And what we're plotting here is the total damping. So that's sort of like the constant linear damping rate plus the nonlinear damping coefficient times the expectation value, the average value of x squared. And that's actually how we generate these data points here.
Yeah.
You can already get a pretty accurate fit by just putting in a power dependent Q. That's also what we did for years. and there's actually almost no difference between the shape of this curve for a power dependent Q, the shape difference with the nonlinear damping versus just a Q that depends on the force you're applying is sort of marginal in the dynamics. It's there, but it's not so super different.
Okay.
So we could fit this with a nonlinear damping model, and it does a pretty good job. And we were patting ourselves on the back, and we were saying, okay, great, we have some nonlinear damping. Yeah, okay, there's a phenomenological model. We don't have any idea where it comes from, but you know, it looks pretty good, except for the last point is a little bit off. But yeah, maybe it's a higher order term. So that was where the status sat for a couple of years. I mean, it's actually quite not true. It's like a 7th order polynomial that we have to solve to get it's also a bit complicated because it's embedded in a cavity. So the power is not exactly like the force of force. Yeah, there's about 7 pages of algebra in one equation to get this fit. But so we were pretty happy that it did a good job, but still we had no idea where it was coming from. So then enters Mario many years later, and he was doing a lot of work in QTIP, and QTIP is this quantum simulation, quantum toolbox package in Python, and it basically allows you to program in whatever you want, add damping of whatever you want, write that as a Lindblad equation to describe the full quantum dynamics, and then push a button. And then it's got some pretty efficient code in the background to do the mega numerical integration of a whole bunch of huge sparse matrices. And it can spit you out an answer. And he was sort of a little bit interested in this, so he started to simulate it. And it turns out that he could already start to reproduce this loss of the depth of the dip when including only linear damping. So he put a Kerr oscillator into QTIP. He didn't put any nonlinear damping. And he just solved it. And what came out was something that looked like it had nonlinear damping in the expectation values. And that was where we were like, huh, that's kind of weird. And then he did a lot of work. This basically he made a fit of this for every single power of all of these data points, constrained by the entire data set to these QTIP Lindblad calculations, which involves running code on a cluster for about a week. and what came out was actually a quite spectacular agreement of the model with the data points, basically with no free parameters, using the independently calibrated Joseph's inductance that we had from the previous measurements, and including no thermal noise as well. Basically, this is at 0 temperature, and it exactly reproduces our results.
So it also predicts the linear damping, or that comes from the calibration, basically.
Yeah. So the linear damping rate we calibrate by the low power measurements, which is then independent of the power independent, line width at low powers, much lower powers, and then the other key parameter is the nonlinearity, and that we calibrate by knowing the Josephson inductance. If we know the Josephson inductance, the only assumption is that our SAS junction is a sinusoidal current phase relation. If that's true, then we actually can predict exactly what the Kerr nonlinearity is. Oh,
cool.
So the upshot is that somehow, if we can also do the simulation. I've made him do this, basically turning off quantum noise if you turn off the quantum noise, the quantum fluctuations of the current in the capacitors, inductors and the charge on the capacitors, then actually you obtain this solid line here, which is basically something which is not included as nonlinear damping. So somehow this confirms that this observation that this amplitude is going, this minimum of the S21 is going up, is related to the quantum fluctuations of the circuit. And this is all without adding any nonlinear damping. So
Wow.
the bag you stir together is just nonlinearity, conservative nonlinearity, quantum mechanics, and linear damping. And what comes out is nonlinear damping. Now, and we were like, wow, this is pretty cool. So it turns out that we can do the best fit constrained by the full data set for nonlinear damping, the phenomenological nonlinear damping with an x squared x dot term. And we can compare that to quantum noise. And actually, it turns out that the quantum noise does a better fit. It's very, very subtle, but actually the quantum noise is a better fit than even the phenomenological x squared x dot. So it looks like the quantum noise is almost x squared x dot, but not quite. So what? Yeah, okay, it's great. We can pat ourselves on the back and say we did a great job. We can put something into a week-long simulation in the cluster and predict our results, which sounds great. But what we want to do is to understand where this is actually coming from. So for that, there is an important concept that is different between a nonlinear oscillator and a linear oscillator. And this is my also first order understanding of a Duffing oscillator. If I look at the Duffing response force, it's this linear response plus this cubic term. I can actually rewrite that as sort of an effective spring constant, which is the bare spring constant plus the Duffing coefficient times the time average value of x squared. And that gives me sort of we can also then write that as you can do Taylor expansion. I can do a Taylor expansion at least sometimes, and you can write that as as a shift of the natural frequency of the oscillator that depends on the oscillator's amplitude. And so a sort of a convenient way to think about and understand the Duffing oscillator is that it's sort of different than a harmonic oscillator, because a harmonic oscillator, the natural frequency is just a constant value. But a Duffing oscillator, because of the change of the average spring constant, it actually has a natural frequency that depends on amplitude. And a very nice illustration of this is actually from the Heidman group. This is some measurements they did with photonic crystal readout of resonators. But the upshot is that they were looking at ring down. I mean, you start your resonator oscillating and you turn off the oscillating force and you look at what happens. And this is what people typically do. They measure the amplitude of the ring down, right, as a function of time, and it goes down. And of course, then they fit this to a line and get the Q. But they were smart enough to push a button on their software to also measure the phase. And if they measure the phase of the ring down, they can also determine the frequency of the oscillator. And so in a linear limit, basically the frequency of the oscillator is not changed when you turn off the force. Here's a funny one. If you have a linear limit, but you're doing off-resonant driving, it turns out that when you turn off the driving, the frequency of the oscillator instantaneously changes to its natural frequency. So because here it's not oscillating as natural frequency, it's oscillating at the drive frequency. But if you turn it off, then it just basically jumps immediately to the natural frequency and oscillates. But if you do this in a nonlinear regime where there's a Duffing response, then what happens is as you turn off the driving force, actually the resonant frequency changes. And that's a reflection of the fact that the resonant frequency is dependent on the amplitude of the oscillation. So that's the concept I want to bring across in your head. What you need is the idea that for a Duffing oscillator, the frequency, there's sort of a natural frequency that determines how fast the phase evolves in the oscillations. And that frequency is dependent on amplitude for a Duffing oscillator. And that's the key difference. Now, what do we need? What does quantum mechanics add to this story? What quantum mechanics adds to the story is that a harmonic oscillator in quantum mechanics has quantum uncertainty in its amplitude. That is what people call photon shot noise, for example. So if I have a harmonic oscillator oscillating in a coherent state, then I do not have a single amplitude, a single photon number, but I have a quantum uncertainty in that photon number, in the amplitude of the oscillator. And actually, as we know, the uncertainty in the photon number, that scales like the square root of the number of photons. So as I drive my oscillator harder, I get more uncertainty in its amplitude. Now we need to connect that to the fact that a Kerr oscillator, a Duffing oscillator, has a natural frequency that depends on amplitude. And actually the amplitude is just directly related to the photon number. So the key is that the coherent state in quantum mechanics has quantum uncertainty in the photon number, and therefore there's quantum uncertainty in the expectation value of x squared. And that leads to quantum uncertainty in the natural frequency of the Kerr oscillator. And that's given by the square root of the number of photons that it's oscillating in my coherent state times this coefficient here. And the key idea is that through the nonlinearity, you translate the uncertainty in photon number into an uncertainty in natural frequency. And the key is that this doesn't happen for a linear harmonic oscillator. So what happens, the upshot of this whole story is that when we start to drive our Duffing oscillator to a larger amplitude, it experiences a quantum uncertainty in its natural frequency due to its own shot noise in its amplitude of its motion. This leads, and what the dynamics shows, we show this in one way by just solving the whole thing in Q-tip. We also did an analytical derivation. A postdoc in my group was very strong in theory. He did an analytical derivation showing that semi-classically the same thing happens if there's uncertainty in the amplitude. If there's noise in the amplitude of your Duffing oscillator, then that leads to a dynamics of the average value that behaves just like nonlinear damping. The upshot is that in the end, it looks like a duck and it quacks like a duck, but it's not quite a duck because it's not actually nonlinear damping, but it's actually nonlinear dephasing that we're looking at. But if we look at only the expectation values, the average values that we measure with a network analyzer, then actually it follows exactly the predictions of a nonlinear damping response. And what was kind of fun is that my student Mario, he took a look at some of this earlier work with the nanotubes, and it turns out that it's possible. You can basically use our semi-classical theory also with thermal noise, and if you just plug in the thermal noise of the nanotube, an estimate of the thermal noise of the nanotubes, that is already sufficient to explain the nonlinear damping that they observed.
Gary, why do you call it dephasing? Does it behave like a set of resonators that each have a slightly different resonance frequency, and you're never driving it exactly at its resonance frequency, because always there's other resonators that have different resonance frequencies.
So that's what, there's two effects actually. One effect is that you're not driving it on resonance, because sometimes it's not on resonance because of the quantum fluctuations. The other effect is that you redistribute. Sometimes when you drive it, it shifts frequency and then emits at a different frequency, and that different frequency is not picked up by your network analyzer.
Okay.
So it results in a redistribution of the power to a broad, and actually it turns out, this is what Mario tells me, it's exactly 50-50 split between those two effects.
And did you try to do a ring down of such a system? Because there you would be able to see if it's really damping or not, right?
Sure, it would have been great, but the ring down is very hard because it's a pretty fast ring down. It's like 200 kilohertz.
But in the simulator, it's possible, right?
Oh yeah, the simulation, sure, yeah, that we can totally do. Yeah, it should be different.
I think with the ring down, you could probably distinguish.
I think you could.
This kind of quantum damping from normal damping.
I think so. Yeah. Unless maybe where the reviewers thought we didn't have enough data, so they were like, yeah, sounds good, but you should really have more evidence. We're like, come on. This data is like 7 years old.
It looks very nice.
So the devices are all dead. They're long oxidized. The whole thing is, so we're thinking about maybe doing some new measurements with new fab, but it's really tricky. So maybe I'm probably over time. How am I doing for time?
It's 1:10, so you're 10 minutes over time. But yeah, I would say continue. I have another meeting at 1:30, so yeah.
Okay, so that's basic. That's the main message I want to get across.
Maybe if people have to leave, they can ask their questions now.
Sure, yeah.
I don't hear anything, so yeah, then just proceed.
Well, I had a question, but I'm not going to.
Yeah. Okay.
Good. So this picture I just showed you is a nice hand waving intuitive picture of this photon shot noise. The shot noise of the oscillator itself causing, resulting in quantum uncertainty of the oscillator's natural frequency. Right? That's kind of that's sort of the hand waving picture I've shown so far. It turns out you can make this more quantitative by using a picture of something called Wigner currents. It's actually a very nice way to understand it in a slightly different way. So to do that, I'll first, I don't know how many of you are Wigner function experts. So I'll first show sort of a crash course on Wigner functions. You can actually read it. You can actually follow I have an undergraduate level course where I explain this in the quantum minor. If you are interested, we have some material online. But it has to do with something called the Wigner quasi-probability distribution. And what this is a two-dimensional plot. One axis is position, or sometimes I quadrature. The other axis is momentum, or Q quadrature. They're actually related for an oscillator. An oscillator, the one quadrature is related to momentum and the other one to position. And the color in here tells you the probability that if you measured the particle, well, it kind of tells you the probability that if you measured the particle, it would have this momentum in that position. And you can kind of see that there's a way of representing it. You can actually mathematically map the wave function onto this Wigner function. And this is actually the Wigner function of the ground state of a harmonic oscillator. And it has it's a little ball. And actually that ball is exactly it's called, I call it a Heisenberg limited ball. Basically, you can see the Heisenberg limit here. There's a quantum uncertainty in momentum and the quantum uncertainty in position. And the product of those two must be h bar. And so whatever kind of wave function I create here, it has to have an area that is limited by this Heisenberg h bar over 2 limit. So yeah, and this is the ground state. If I create a coherent state, if I start to make this harmonic oscillator oscillate, then what would happen is that this ball would move out. I wish I'd had an animation, but I don't, so you have to follow my mouse pointer. This ball would move out, and then he would start to spin around. because for an oscillator, the momentum and position, the momentum, it gets translated to position, and then it starts to, it speeds up in the middle, and it slows down at the other edge, and it speeds up in the middle and slows down at the other edge. So basically, this ball would just spin around. Now, what we typically do is go to a rotating frame where we translate so that that spinning is canceled, so the ball is then sort of static. But okay, before we start thinking about driving this harmonic oscillator, you can actually phenomenologically understand, in a nice intuitive way, understand why the ground state looks like this by looking at two forces that cause this ball of density to evolve. These are called Wigner currents. And there's one force, which is quantum noise, and that pushes basically outwards. It causes the ball to diffuse outwards, and that is like an arrow pointing outwards. And then the other one is damping, and that pushes the ball inwards. And this sort of it's actually the balance between these two that gives us this ground state, which is this ball. So now we're not even at the Kerr oscillator yet. This is even just understanding a driven harmonic oscillator in this picture. It's actually really fun, but a bit complicated. So what this picture shows you here is our best attempt at trying to explain to you how these balances work in a driven harmonic oscillator. So what I showed you before would be a ball over here. Sorry, the axis labels are caught, but this is 0. And now we've applied a driving force which pulls the ball outwards. Of course, in the rotating frame, it would also make it spin like crazy, but we've gone in a lab frame, it would spin like crazy. We've gone into a rotating frame, so the drive is just pulling the ball in one direction. And what happens is that, the ball gets pulled outwards. The driving force is balanced by dissipation, but dissipation pulls you back to the origin. And so then the question is, why is there still a ball? And the reason is still a ball is because the quantum noise here balances differently at the different points and produces then for a harmonic oscillator a steady state that is just a ball that is displaced. So that's the complicated, but hopefully in a few minutes useful description of how to understand the steady state of a purely linear driven harmonic oscillator by balancing all of these Wigner currents. So what we need to do is add Kerr, nonlinearity. And so what nonlinearity does, this is a picture that includes only the Kerr. So there's no driving and no damping. We're just imagining that somehow we have a ball that's displaced, and I start over here. I initialize it at some ball over here, and then we let Kerr act on the state. What Kerr will do is that it creates a frequency shift that is proportional to the amplitude. That's what I said before. And so if this is the origin, points that are closer to the origin will move slowly. Actually, in the rotating, this is again in the rotating frame of the linear oscillator. So if there's no Kerr, the ball would just be constant. But because we've displaced it, actually we get an additional rotational term that is proportional to how far we've gone away from the origin. And what that does is it takes our nice little orange and squeezes it out into sort of a banana. The ones that are closer to the origin move more slowly, and the ones that are further from the origin move more quickly, actually, in the rotation circle. So actually, if you left this longer, eventually there'd be craziness happening and you would get a Schrödinger cat state. But we're going to talk about the case of dissipation in a minute, which will actually stop us from ever reaching the Schrödinger cat. But the basic idea is that the first order, what will happen to the Kerr is that it will cause this sort of elongation and twisting of this initial round ball. So now what we need to do to get all the ingredients of our circuit is that we need to add dissipation, which is going to be a Wigner current force pulling us back to the origin. the further you are from the origin, the longer this arrow is, because the harder you're pulled back to the origin. That's damping. And then we add this, we're going to go into rotating frame of the care, the average care shift, so that we're not spinning all the time. And then what will happen is that the ones that are closer to the origin will get pulled downwards. We're going into the rotating frame of this average spinning banana. And then, or croissant, as my French PhD student prefers to call it. And what will happen is that it will sort of pull these two guys out. So it'll pull the ball upwards this way and downwards that way. And the steady state is when you balance this damping, this care, and the contribution of the quantum noise. And the upshot, what we calculate in the experiment is how much the average position changes, and that's the shift of the ball from here down to there. So that's what we measure. We measure this tiny little displacement, and that is what we've based all of our that's the whole basis of the observations and theory that we've compared our data to. Now, of course, there's some very interesting things in this plot, and in particular, actually, of course, this ball has gotten squeezed into this banana.
So Gary, this is the sum. You're describing what comes out of the simulations of Mario's software, right?
That's right. Yeah.
Yeah.
Well, Mario's code.
Yeah. Okay.
So this is basically what's predicted by the Lindblad equation for the steady state, and what you get, of course, is that actually the noise is squeezed. And actually squeezed by about 0.8 below the quantum limit. So actually this will generate squeezing. And that would be super cool to observe, of course. And I think it's probably what the referees want us to see. But which would be awesome. But one of the problems, of course, is that in our real measurements, we're working with Hempt amplifiers, which add about 20 photons of noise on top of the signal. And then the squeezing is very, very difficult to observe. Okay, so give a summary. I've talked about our observations of nonlinear damping in a driven calibrated quantum Duffing oscillator. We've shown using the theory that this emerges, the theory and the calibrations that this emerges purely from quantum fluctuations and a conservative nonlinearity. And we've given two pictures on how to see how this arises, and resulted in an interesting prediction that this should have quantum squeezing of the noise. And that is what I set out to tell you today.
Great, thank you, Gary. Yeah, very interesting presentation. I don't know, are there questions?
Yes.
Okay.
I want to learn about, so you talked about some kind of analogy between the mechanical, like classical mechanical systems and this happening. So I thought, like, would this be the case if we just had any Duffing oscillator and we put a bit of a noise on top of our forcing term, and we see the same thing, right? Okay, so I understood correctly. Then what should be
that's actually one of the, it's an interesting thing. I mean, I remember going to talks with Michael Rukas years ago, and he's obsessed with dynamic range. And he defines dynamic range as the point where we hit this Duffing nonlinearity. And at some point I was like, okay, why should you care, right? And I think that this is actually the reason you care, because what happens is that any noise in the amplitude that you're driving it with gets translated into frequency noise for a Duffing oscillator. And since for NEM sensing, you're looking at frequencies. Oh, hold on. Since for Duffing oscillators, you're looking, for mass sensing, you're looking at frequency shifts, then actually whereas for a linear oscillator, the amplitude noise has no effect on your measurements. Hold on, I might have to take this. No, in a sec. Yeah, I think that's the real reason why people are obsessed with dynamic range and don't like to avoid nonlinearity in NEMS sensors.
So Gary, it's a kind of nonlinear fluctuation broadening, right?
Yeah, exactly.
Yeah.
I think this is
but
actually exactly the same thing, but then from quantum fluctuations.
Yeah, nice.
But what about the relationship between the force and noise? So is it like linearly increasing, or like how should the noise act when you're increasing the force? Because you can put any noise on top of the force, and your nonlinear damping term will be different then, I think.
Sure. Yeah, exactly. So the nonlinear damping comes about because of the fact that the quantum amplitude noise scales with the amplitude of the state, right? So let's say if you have if you have a generator and the only noise is the thermal noise of the generator that's relevant, then you should be fine. The typical problem that we experience all the time is that when you go to very large drive powers, what you're limited by is what the sideband noise is, the carrier phase noise or amplitude noise. And the problem with that is it's proportional to the carrier. So as you turn up the power of the carrier, the power of the noise also goes up. And then it's
then you shouldn't see any effects of this nonlinear damping in a ring down, because you're not forcing it anymore.
Well, let's say, first of all, you should let's say in our case, because the noise arises from the quantum state itself, right? We will always, even if we're not forcing it, that quantum state will still have that noise. But your point about ring, this is also what Peter mentioned earlier, the ring down is a super good idea, because what we're actually seeing is something that's dephasing, and that should not affect the energy ring down time. And so technically, we have papers about this many years ago ourselves even, technically, we should see that the energy ring down time is not affected. And that would be a great way to distinguish. In fact, I remember even trying to get Shun to do the energy ring down measurements years ago, but it's super hard measurement. It involves a whole bunch of hardware and software that we didn't have at the time. And yeah.
Thank you.
No problem.
Oh, I think my next meeting is starting in a few minutes. But I don't know if there's urgent other questions to Gary.
A quick one.
Yeah.
So you always assume this kind of like zero temperature, but would it make a difference, for instance, if your quantum fluctuation was a little bit temperature dependent, like say you're not at 10 millikelvin, but like 1 Kelvin, let's say, and you kind of increase that amplitude of that fluctuation amplitude a little bit?
I believe that we've even put the temperature in as a fit parameter. Of course, actually, this is Achilles' heel a little bit, is that if we happen to miscalibrate our nonlinearity, then it may be that we're actually at 100 Kelvin or something, right?
Yeah.
Let's say, so that's why, the whole thing does rely on a good estimate of the Joseon inductance to independently calibrate the nonlinearity, because the temperature and nonlinearity just play, they come in as a product. So but let's say if we believe that we've calibrated the nonlinearity correctly, actually we can use our observations to calibrate, or at least provide a lower bound of the temperature. And I believe that's even what we did, and it is something like something small.
Okay, I was thinking even it's a way of kind of tuning that fluctuation and just kind of being able to just test your model in different ways, as long as you're below TC, right? Or
yeah, exactly. No, that's sort of what I mean. Actually, our mode temperature could be much higher than TC too, right? We can add lots of noise in our electromagnetic mode, and we can add 100 Kelvin if we wanted to, if we don't attenuate properly, without going above TC, right? But that's why the whole thing relies very much on this calibration of the absolute Joseon inductance, and that's why it's so crucial to do it really carefully by doing it because actually, even strictly speaking, the inductance that the circuit sees depends on the position of that junction. That's why you have to do the full sonnet, where the lumped element inductor is at the exact geometric position of the real junction. Yeah.
Thanks. Yeah, super interesting.
Yeah.